Hello everyone, and welcome back to the mathematics lecture on binomial theorem and its applications. This is the third lecture in the sequence, and brief recap, very brief recap of what exactly is the binomial theorem. Sorry, I am doing this again and again, and this was the statement of the theorem, right. In the last class we found out that these two are equal, these two are equal, the sequence goes like this, comes back like this, and they are mirror images of each other. Whether you write it as x plus y or y plus x, the answer should be the same. Okay. That is one thing we noticed. The other thing that we noticed is that if I plug in x equal to y equal to 1, you can plug in x equal to 1, y equal to 1, you get 2 power n on this side, but on this side you get n c 0 plus n c 1 plus n c 2 plus n c 3 all the way till n c n, right. So, that is the second result, that the sum of all of these is 2 power n, right. Of course, you also know that this equal to this, this equal to this equal to that, right. So, if my n was odd, then my total sequence, half of the sequence would have been equal to the other half of the sequence. The sum of them is 2 power n. So, each of the sets is 2 power n minus 1 if my n was odd, but all right, forget n equal to odd. What if you plug in x equal to 1 and y equal to minus 1? If you plug in x equal to 1 and y equal to minus 1, your net result is 0 and you get n c 0 minus n c 1 plus n c 2 etcetera etcetera, right. This is also a result, and then you put some of them on the left hand side, some others on the right hand side. So, the sum of the even terms is equal to the sum of the odd terms n c 1, n c 3, n c 5 and so on. Okay. So, this was another result that we saw. Then we did something else, and we found out the coefficient of x plus 1 by x whole to the power 2 n, and we found that in this expansion there is only one term which does not have an x. There is only one term, and that is the middle one, and the middle coefficient is 2 n c n. And then what did we do? We broke this up in a different way. We said maybe we can write it as x plus 1 by x whole power n times 1 by x plus x whole power n, right. And what is the coefficient of the term which does not have an x in it? So, you expand one, you expand the other, and then you find out that n c 0 squared plus n c 1 squared plus n c 2 squared and so on, that has got to be equal to 2 n c n. You can generalize this a little bit further, and we got the above result: n c 0, n c r, n c 1, n c r plus 1 shifted 1, n c 2, n c r plus 2 and so on, that is equal to 2 n c n minus r. So, this was also a result that we got. And then we were doing some problems which do not necessarily use these results in a straightforward way, but we were doing some just a few problems. Okay. One problem, one more problem that I have in my kitty, and let us try this. Okay. This problem happened to have been in one of the JEEs. Okay, JEE problem. How do you solve this? This is actually not very hard. A minus b whole power n. Break it up, the sum of 5th and 6th terms. What is the first term? You choose all n's and all a's and no b's. You do not choose any b's. plus n c 1 times a power n minus 1 b, that is the second term, right. Then comes the third term, fourth term, fifth term. What is the fifth term going to be? N c. So, the first term is n c 0. So, the fifth term is going to be n c 1, n c 2, n c 3, n c 4, and therefore, you are going to choose n minus 4 A's and how many B's? 4 B's. That is why n choose 4. You are choosing 4 B's. So, that is the fifth term. And what is the sixth term? Oh, mistake. I forgot the minus. So, you are not doing a plus b, you are doing a plus minus b. So, this b comes with a minus. If I just have a b, it comes with a minus, b squared comes with a plus, b cube comes with a minus, b power 4 has a plus in front, and then b power 5 is the sixth term. So, this is the fifth, and the sixth term is minus n c 5 a to the power n minus 5 times b to the power 5. That is my sixth term. And the question says that the sum of the fifth and sixth is 0, which means these two. So, that gives me n c 4 a power n minus 4 b power 4 is equal to n c 5 a power n minus 5 b power 5. All right, and then simplify. And what is n c 4? And what is n c 5? And then once again simplify. N factorial goes away. 4 factorial is 1 times 2 times 3 times 4, and 5 factorial is 4 factorial times 5. N minus 5 factorial, n minus 4 factorial is bigger than n minus 5. N minus 4 factorial is n minus 5 factorial times n minus 4. Which leads me to a by b is equal to n minus 4 by 5. Okay? That was a quick JEE question for you, quite straightforward. All right, let us do another one. So, this is the problem statement, that 1 plus x squared whole to the power n is equal to a 0 plus a 1 x plus a 2 x squared. All of those terms are there, and you know the largest term is going to be x power 2 n. Okay. X power 2 n is the largest term, and for x power 2 n he has used a coefficient of a 2 n in the question. He is saying that this is given to you, and then so this is my question 1. How will you do it? How will you do this? Oh, come on, this is very straightforward, just like our the way we had done this. Remember, we plugged in x equal to 1, y equal to 1, and all of these disappeared. We were left only with NC 0. This is 1, this is 1. So, what will you do? Just plug in x equal to 1. If you plug in x equal to 1, a naught plus a 1 plus a 2 all the way till a 2n. So, what is the answer? 1 plus 1 plus 1, 3 whole power n. Okay. So, that is a very straightforward question. Question 2. What is this sum? A naught minus a 1 plus a 2 minus a 3 plus a 4. So, this term has to be a minus, this term has to be a plus. What does it remind you of? X is equal to minus 1 will do the job, right. A naught minus a 1 plus a 2 minus a 3 and so on and so forth. Okay. So, just plug in x equal to minus 1, and if you plug in x equal to minus 1, 1 minus 1 is 0 plus minus 1 squared is 1. So, the net result is a 1 whole power n. So, your answer is 1. Okay. Very interesting. All right. Then I have got a third question for you. How will you do this? Let us check. You have to plug in some x, right. So, what are you going to plug in? You want to plug in x equal to, okay. So, one possibility is that you look at this and multiply it with a 1 by x. Okay. This is one possibility, because this, the first one, is going to expand out, and what will you get here? You will get a 0 plus a 1 x plus a 2 x squared plus so on all the way till a 2 n x power 2 n. Okay. But the second one is going to expand out, and here instead of x I am writing minus 1 by x instead of x, right. So, if I write minus 1 by x instead of x, I get a naught minus a 1 by x plus a 2 by x squared minus and then plus a 2 n by x power 2 n. Okay. That is the second term. Okay. And if you look at in the product of these two expressions, you are taking the product of these two expressions, what is the term that is independent of x? No x. So, if I multiply this a naught with any random term, I will have some x in that random term unless I multiply it with this first one. So, if I multiply these two, then I get something independent of x. Okay. A1x, if you multiply A1x with A naught, you have got x. If you multiply A1x with A2 by x squared, you are ending up with 1 by x. Any other term you will still have an x inside. The only situation where A1x will multiply with something and you will not get an x is if you multiply with minus A1 by x. So, you multiply these two, right, that will give you minus A1 squared. How about A2 x squared? If you multiply it with A naught, x squared remains. Multiply with A1 by x, x remains. Anything else, there is some x component in it, except if you multiply with A2 by x squared, okay, and so on and so forth. So, in this expansion, the term independent of x is the question. Okay, that is the only term which is independent of x. Okay. How else do you construct that? So, I found out that the term independent of x is this. Now, I have to multiply the two in some other way and find the term independent of x. What is the other way? The other way is I pre-multiply and then do whole power n. Let us pre-multiply. So, just by the way, this is guesswork. Is intelligent guesswork. So, this is where your practice will pay. The more you practice, the better you will be at guessing what should be the way to go about solving this problem. Otherwise, you will be stuck, right. You have to intelligently guess this construction. Okay. So, let us try this out. 1 plus x squared whole power n into 1 minus 1 by x plus 1 by x squared whole power n. And in this I am looking for the term that is independent of x, just to remind you. So, what we are going to do is we are going to take n out . Okay. And you know how to do this multiplication. So, you can do term by term, or you can do a plus b times a minus b, in which case you get 1 plus x squared. Oh no, you can't do that. So, let us do term by term. I have a 1 minus 1 by x plus 1 by x squared. So, I multiplied 1 with all these 3 terms, then I take the x and multiply with all these 3 terms. And finally, I take the x squared and multiply with these 3 terms. And then there is a lot of cancelling out. This 1 by x cancels out with the next one, the x cancels out with the minus x, and there is a minus 1 that cancels out with a plus 1, although one of those 3 remains. 1 by x squared plus 1 plus x squared whole to the power n. Okay. Recollect the question, 1 plus x squared whole to the power n was given as a naught plus a 1 x plus a 2 x squared plus so on a 2 n x power 2 n. So, if this is what is given, what is going to be 1 by x squared plus 1 plus x squared whole power n. It is a little hard to predict what it is going to be unless we take things common outside. So, let us take 1 by x power 2 n common outside, and then what remains is a 1 plus x squared plus x power 4 whole power n, and I have got it in the same format, right. The format is the same, which means that this is equal to 1 by x power 2 n times a naught plus a 1, the format where x is equal to x squared. So, a 1 x squared plus a 2 x power 4 plus dot 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 a 2 n x power 4 n. Okay. And what am I looking for? I am looking for the term that is independent of x, which means that somewhere inside this there is a term with x power 2 n, and that term will be independent of x because of this outside 1 by x power 2 n. Okay. What is that term? That is the nth term, right. A 0 x power 0, a 1 x power x squared, 1 times 2, a 2 x power 2 times 2. So, what is going to be x power 2 times n? The coefficient is going to be a n. Fine. So, the term independent of x is nothing but a n, and my question was, so the term independent of x in this expansion is a naught squared minus a 1 squared plus a 2 squared minus a 3 squared, and I did it in some other way. I first multiplied then raised to the power as opposed to raising to the power and then multiplying, right. And what did I get? I got this as a n. Okay. The clue over here is this intelligent guesswork. I am sorry, this guesswork cannot be taught, it comes only with practice. The more you practice, the better you will be able to make these guesses. Okay. So, let us try yet another one, 1 plus x whole to the power 14, whole raised to the power 14. Okay. And the question is that if the rth, r plus 1th, r plus 2th terms are in arithmetic progression. You know what arithmetic progression is? I hope you know what arithmetic progression is. Okay. So, rth, r plus 1th, r plus 2th terms are in arithmetic progression. Then what is r? It is a straightforward question. Let us try it out. AP, what it means is that that the sum of these two terms, if these three are in AP, then rth term plus r plus 2th term will be 2 times r plus 1th term, or in other words r plus 1th term minus rth term will be equal to r plus 2th term minus r plus 1th term, right. So, what is the rth term? What is the first term? The first term is 1, right. You choose all 14 ones, no x's, that gives you the first term. The second term is you choose 13 ones and 1 x. The third term is you choose 12 ones and 2 x's, right. So, the rth one is you choose how many ones? The rth term you are going to choose 14 minus r plus 1 ones, and how many x's? You are going to choose r minus 1 x's. So, the term is going to be 14 choose r minus 1, 1 to the power 14 minus r plus 1 is just 1 times x power r minus 1. So, this is the rth term. Okay. Likewise, what is the r plus 1th term? It is the next term, 14 C r x power r. And what is the r plus 2th term? 14 choose r plus 1 x power r plus 1. Okay. So, he says that these 3 terms are in arithmetic progression. What is 14 C r minus 1? Factorial 14 by factorial r minus 1 and factorial 13 minus r. No, 15 minus r. Okay. So, this is the 14 C r minus 1. This is the r plus 1th term, and this sum is equal to 2 times 14 factorial by 14 minus r factorial x power r. So, this is pretty much the problem statement, and we have to find out what is x in terms of what is r in terms of x, obviously. So, one thing you can do is you can scratch out the 14 factorial from everywhere. The next thing you can do is you can scratch out x power r minus 1 from all over the place. Okay. Next, what you can do is, which is the least one, r minus 1, r plus 1 or r. The smallest is r minus 1. So, you can scratch out r minus 1 factorial all over the place, and here you will get r plus 1 times r, and here you will get r. And then further, what do you want to scratch out? Which is the smallest over here? 15 minus r or 14 minus r or 13 minus r? 13 minus r is the smallest. So, you can scratch it out completely, and over here you get 14 minus r, and over here you get 14 minus r into 15 minus r, and now things are simpler to work with. So, you have got a much simpler, much more straightforward relationship, right. So, my relationship now is 1 by 14 minus r times 15 minus r plus, from the second term I have got x squared by r into r plus 1, and from the third term I have got 2 x by r into 14 minus r. And now you have to solve for r. Okay. So, hopefully you can do it, multiply by 14 minus r maybe. Okay. I am going to leave you to solve the rest of this, because this is a straightforward application of algebra. So, we are not going to pursue this any further. So, these are the kind of questions that you are going to find typically coming up when we discuss the binomial theorem. Okay. Now, we are going to generalize a little bit, because we have a lot more to do. So, I go back over here, x plus y whole power n is n c 0 x to the power n, n c 1 x power n minus 1 y, n c 2 etc. Okay. The generalization is that n, this formula, right now this formula is for n as an integer, positive integer. It turns out that the same formula will work even when n is not an integer, all right. Even when n is not an integer, something similar will work, not the same, but something similar. Let us rewrite it, 1 plus x whole power n. So, this is going to be equal to n c 0, and what is n c 0? Factorial n by factorial 0 factorial n plus n c 1 times x, which is factorial n factorial 1 factorial n minus 1 times x plus n c 2 times x squared Okay. So, this is a 1, and what is this? Factorial n by factorial n minus 1 is just an n. Factorial n by factorial 2 factorial n minus 2 is nothing but n into n minus 1 by, this is 2 into 1. And the third term is going to be n into n minus 1 into n minus 2 times by factorial 3. Okay. So, I am just rewriting the binomial theorem, it is just a rewrite so far. Now, it so happens that if you plug it in this form, if you put it in this form, this is 1 plus x whole power n. This form of the binomial theorem is valid even when n is not an integer, as long as, so this is, there is one condition, right, as long as you play by this rule, that as long as I am going to keep magnitude of x to be less than 1. As long as you play by this rule, then this statement is valid even when n is not an integer. N can be anything, n can be a fraction, n can be positive, n can be negative, whatever you want, you plug in there, it is going to work. So, this is a generalization of the binomial theorem. Of course, you are going to say what is the proof of this? The proof of this is going to come from Taylor series. You are hopefully going to study Taylor series when you study calculus. So, we are not going to do the Taylor series, we are going to use this as a generalization of the binomial theorem. Okay. One possible use, I do not know what is the level of calculus that you have studied so far, but let us assume that you have at least studied till limits, right. So, one possible use is you might have studied this relationship, limit x tends to 0 e power x minus 1 by x. You would have studied this one. Look, I mean we have already covered the basics of binomial theorem, right. We are now going into more serious applications. We are extending the binomial theorem, and the reason why we are extending the binomial theorem is because we want to solve a variety of problems, and to be able to solve a variety of problems you have to be open minded, you have to throw away the boundaries between algebra and arithmetic and calculus and geometry. All these boundaries are broken, you are now trying to solve a variety of problems. Okay. So, some calculus you possibly have already studied, and we are going to borrow from the calculus, and this is one result that you might know already, e power x minus 1 by x, limit of that as x tends to 0. You know this is equal to 1. This is one of the standard relationships, limit relationships that you would have studied. Okay. So, if you have studied this, you can rearrange this, right. You can rearrange this as you multiply x on both sides. So, e power x minus 1 limit x tends to 0 is equal to limit x tends to 0 of x, okay. Or in other words, you add 1 on both sides, okay, and then you take to the power 1 by x on both sides. Okay. So, this is a standard definition of E. So, a standard definition of E is that E is limit x tends to 0 1 plus x whole to the power 1 by x. So, you make x smaller and smaller and smaller, keep computing this, and you will converge towards the value of E. The answer for E of course is 2.71828182848, whatever it is, right. Okay. It is like E is a number like pi, right. So, this number is defined as E, and E is very popular when it comes to taking powers and taking logarithms. I could also have written it in this format, limit y tends to infinity. So, y is a very large number, 1 plus 1 by y whole power y. So, I have replaced x with 1 by y in this formulation. Okay. Suppose you want to compute e to the power x. Okay. 1 plus 1 by y whole to the power x y. Any problem? No problem. Limit y tends to infinity. How will you work this out? 1 plus 1 by y, remember 1 by y satisfies right. I am not calling it x anymore, I have called it y. So, 1 by y is certainly smaller than 1. Okay. If 1 by, because 1 y is tending to infinity. So, 1 by y is certainly smaller than 1, it is very small. Okay. So, it satisfies that relationship, which means that 1 plus something which is very small, smaller than 1, raised to some power. To solve this, I can use my binomial theorem, or rather the extension, the generalization of the binomial theorem, right. It is conceivable that I just plug in whatever is the value of n, x, etc. into this and work it out. Okay. So, what is my n in this case? So, let us write it as capital X, right. 1 plus x, I have put a capital to the power n is 1 plus blah blah blah. So, this n has to be x y and capital X has to be 1 by y, and after that I just plug this in. And of course, limit y tends to infinity remains. So, the first is 1, next is n times x, where n is x y and x is 1 by y. So, this becomes just an x plus n x y times n minus 1 by 2 x squared, x is 1 by y plus okay. So far so good, and now we are almost there. We just declare the limit y tends to infinity, y is very large. So, you have got x times y minus 1, the whole thing by y squared. So, this is x squared y squared by y squared, which is x squared, minus x y by y squared, which is very small. So, this entire term is going to behave as if this minus 1 portion was not really there, because y is very large, right. Likewise, this minus 1 portion, this minus 2 portion are going to be negligibly small, because they will have to be divided by y squared, y cube, right. Each will be divided by a y, right. So, net result is going to be, sorry, I need a position where you can see it. So, the net result is going to be the second term was x, the third term is going to be x y by y squared. So, x squared by 2 factorial plus x y minus 1 x y minus 2 by 3 factorial y cube. So, these terms go away, y's go away, I get x cube by 3 factorial, and then I will have x power 4 by 4 factorial, and so on and so forth. And of course, limit y tends to infinity is irrelevant, because there is no y inside this. So, I do not have to bother about this. So, this whole thing is e to the power x. So, we arrive at a series e power x is 1 plus x squared by 2 factorial, x cube by 3 factorial, x power 4 by 4 factorial, and so on and so forth. E power minus x, just plug in x equal to minus x, of course, you get 1 minus x plus x squared by 2 factorial minus x cube by 3 factorial plus x power 4 by 4 factorial, and so on and so forth, right. And what is E itself? Just plug in x equal to 1. If I plug in x equal to 1, what do I get? 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial plus 1 by 4 factorial, and so on and so forth. Okay, you work it out, 2.5, 2.77, right, and then so on and so forth. Okay, so before wrapping up our lecture for today, let us just do a few more problems, and there are a lot of identities with the binomial theorem. So, I am going to try to solve a few of them. So, one of them is to prove that. So, this is the question. The question is, prove that C 1 plus 2 C 2 plus 3 C 3 plus all the way till n C n is equal to n times 2 power n minus 1. So, this is the question. Will you be able to do it? How will you do it? So, earlier what did we do? Earlier the one was C 0, we started from C 0 over there, plus C 1 plus C 2 plus C 3 all the way till C n. And what did we get? How did we do this? We did 1 plus x whole power n, right, and then plugged in x equal to 1, right. If you think of 1 plus x whole power n, plug in x equal to 1, you get this as your expansion, right, this as your expansion, and the answer is 1 plus x whole power n, x equal to 1. So, 2 power n. Okay. So, this is similar, but not quite. You do not even start from C 0, right. Look, C 0 is gone, right. You start from C 1 and then 2 C 2 plus 3 C 3 plus etcetera all the way till n C n, and look at the answer, n to the power 2 power n into 2 power n minus 1. Does it kind of remind you of something? Does it remind you of, let us say, d by dx of x power n is n x power n minus 1? Does it remind you of that? It does, does not it? It reminds you of d by dx of something to the power n, which is equal to n x power n minus 1. So, that is the clue, right. So, a lot of times these clues pop up here and there, and you have to take that cue and you have to realize that this problem can easily be solved with the help of one differentiation. So, what are we going to do? We know that 1 plus x whole power n is equal to C 0 plus C 1 x plus C 2 x squared all the way till C n x n. Okay, this is something we know, and do a differentiation. Why am I doing a differentiation? Because I had a clue over here, that is the only reason why. Okay, right now I am just going to do a differentiation and see what comes out. So, I do a differentiation, let us differentiate both sides. So, I get n times 1 plus x whole power n minus 1 times the derivative of what is inside, which is nothing but 0 plus 1, right. So, that is just a 1. So, I differentiated the left hand side. Now, if I differentiate the right hand side, differentiate C 0, you get nothing, again nothing. C 1 x, you get C 1, C 2 x squared, you get 2 C 2 times x. Next one you will get 3 C 3 times x squared, and so on and so forth, all the way till n times C n times x power n minus 1. And now guess what? What do you have to plug in? X equal to, look at the answer, x equal to 1. So, plug in x equal to 1, you get 2 power n minus 1 times n, and that is equal to C 1 plus 2 C 2 times 1 plus 3 C 3 times 1 squared. All right. So, was that nice? If you had not done the differentiation, you would have been roaming around with this problem. Okay, let us try another one. So, this is what I have, and eventually you have to show that this is equal to n plus 2 power n minus 1. So, there are actually two nice ways of doing this. Okay. The first one, what do you think? This is very easy, right? This is equal to C 0 plus C 1 plus C 2 plus so on, plus C 1 plus 2 C 2 plus 3 C 3 plus n C n, right. And you know that you know what is the first one. The first one was 2 power n, and the second one was just what we computed just now. And there you go. Okay. So, you could do it like this, but a lot of times these neat simplifications do not pop up in our head at the right time. At an exam, you are going to look at this, and then if this does not occur to you, or you had forgotten this this expansion, the second expansion, then it does not work out. So, this is a good shortcut. This is a very nice way of doing things, but unfortunately this might not be the first way you think of trying to solve this problem. So, let us try to solve it in one more way. So, maybe you can look at it in this fashion. So, this is what you have, and can I write it backwards? Okay. So, let us say this is k. So, this is also equal to k, and then what you have to realize is that C 0 is the same as C n. Remember, C 0 is the same as C n, C 1 is the same as C n minus 1, C 2 is the same as C n minus 2, C n is the same as C 0. So, when you add these two, you get 2 k on the right hand side, and on the left hand side you get C 0 times n plus 2 plus C 1 times n plus 2 plus C 2 times n plus 2 and so on all the way till n plus 2 times C n. Therefore, k is equal to n plus 2 by 2 times C 0 plus C 1 plus C 2 all the way till C n, and this is something that you know, this is equal to n plus 2 by 2 times 2 power n. So, you have got the same answer. Okay. So, let us stop this lecture here. We solved a variety of problems. We will solve even more problems in the next class. Thank you.